Hi there. It's 5 after, so let's get going. I guess I didn't notice the May Day holiday. So I kind of scheduled the class this weekend, probably. That's why many people aren't joining. My apologies, but let's get going. Maybe we can get to some of the easier parts of the homework and then continue to work through the rest of it over the next sessions.
Okay.
So with that, Mochan, you want to?
Yeah. I'll share my screen and we can get started.
Yeah.
Let's see. Okay. You guys can see my screen, right?
Yes.
Okay. So yeah, before I start, I definitely underestimated the homework. So there's a lot of gaps that I haven't figured out. So yeah, and it's probably good that we can solidify it for next time. But I'll go over what I have so far today, and then we can have discussions, and then it will also be points for me to look into. Yeah, last week was a busy work week also, so this week should be I should have more time for it. Okay.
Yep. So one comment, Mochan, is I think I agree with what you said. The homeworks are even more complicated than I originally thought. And so with that in mind, the thing I wanted to mention before we even get going is two things. One, feel free, given how complex these things are, feel free to look at the solutions that are provided and kind of incorporate, because at least in having attempted it and then gone through the solutions, I would say even understanding what has been coded in the solutions is, it's likely to take quite a bit of time to go through and understand the key parts, even when you're not coding it from scratch. So I think it's okay given the audience, meaning, number of people and how complex some of these things are, that as we move forward, even if you just refer to the solutions and take us through that after having played with it yourself, that's fine. Second point I wanted to make is, as with many other courses we've gone through, we'll take the time. Just because there is a schedule that I've published, the schedule is a guide, and it's more important for us to understand what we are going through. So from that perspective, let's take the time to go through it and grasp what the solutions are offering or what the answers are, rather than rushing through it with the intention of, we only have 2 sessions, so we need to fit it all in. Because from what I can tell, the code is not obvious, and it's better for us to go through it to really grasp what's going on.
Okay. Yeah, that sounds good. Yeah. So I think question number 1 and 2, I've only tried the first 3, so I'll try to go over it, and then I think there'll be a lot of questions and unknown things, and we can just kind of keep tab of them, and I'll look through them, and we can have further discussions next week on those.
Sounds good. Thanks.
But yeah, so let me go over some of the things. I'm right here in PyCharm, and the homework is here also. I kind of like to do the work in PyCharm, like in Python, so that I can add like a breakpoint and look at what's going on in the data. I know you can also do that with the notebook also now in PyCharm, but the window gets kind of messed up, and there's like it's kind of it's not quite designed for it. But I'll try it more next time, see if I can if I can make better use of this, because I think I can still add breakpoints here somewhere. Maybe not. I thought you could. but I'll look more into it. But what I did was basically I implemented it here, and a lot of the stuff was copied over, and so then it's the same thing. So I'll like flip between this back and forth, but it is essentially the same code. Is the font small? Do you want it to be bigger?
At least for me, a little bigger would be good.
Okay.
A little bit, not too much, but just a little bigger. But we can, at least we can see it.
Okay, let's see where I can, font is somewhere here. Okay, here's font. Let's see. 18. Oh, that didn't work. Okay, I don't know.
Yeah, that's okay. Keep going.
Okay.
I think.
Okay, so this might be. So first, I wanted to just go over the question, and then oh yeah, the first thing I wanted to do was if you wanted to run it locally, like I have on your computer, what you need to do. So all you basically have to do is clone this repo, and the package they use here is in here called DPUL, and then the homeworks are over here, and so you can just copy this, do the unzip of the homework, and then pip install in your environment, and then that's all you have to do. So there's nothing else that needs to be done. So this one is pretty straightforward to do. Okay. So let me go to the solution. So the first question is that we will train a simple generative model on discrete 1D data. And so here's the data set, and we have two types of data set. This is data set number 1, and this is data set number 2. So it has 2 peaks. And this is the training data set, and this is the test data set. Right. So let's go over here, and this is the code for it, visualize. And let's not, I mean, if we just go into it and kind of see like what actually is going on, I'll just do a quick description of it so we know what's going on. So D here is the number of bins in the histogram. So D equals 20 means that your training data will have 0 to 19 or 1 to 20. I forgot which one, but I guess we can just do a breakpoint and then run it, and then let's see here. Here's the data. So and it's I don't know where I am. I'm in the right place. Okay, let me just do this again. Okay, so it's here in Q1 sample data, and here we'll see the training data, and it's yeah, between here's the data, kind of a messy way of looking at it, but it's all between 0 and 19. And so this is our training data of 1,000 points or 800 points and 200 points of testing data. And if we look at how it was generated, it's just randomly generated. So just generate a whole bunch of random numbers, right? And then this is the digitized, just means that you make 20 spaces between 0 and 1, and whichever one it falls into, it will get that index, and then we'll just generate it. So this is just a sequence of random numbers between 0 and 19. So yeah, and then this is used to create the histogram. So if I continue on, this is the histogram. This is the training data, and this is the testing data. It's normalized to 1 for both the training and testing data, right? So, and it's the same process for this one, but the D is 100. So there are 100 different values you can take, and it's simple. There's 2 random numbers, and it creates two different peaks. So if I run it real quick, yeah, let's do that. We can see this is the oh, there's more stuff going on here. Okay, so this is the two different. This is the first distribution. This is the second distribution, right? So just exactly as in the homework, these two show up, right? Okay. So here's the first problem. So we'll have theta equals theta 0 to theta 99, R 100. So here I believe this 100 is the D value here. So in this case, so it's 100 in the second case. In the first case, it's 20. So this should be D. So for each bin, we have 1 parameter, theta, right? And then we'll just do a softmax. And so we'll use maximum likelihood via stochastic gradient descent on the training set with the thetas starting all initialized to 0. Right, so so how would we do that, right? So this is sort of basic PyTorch. So let me go into really just a basic 5-minute on how you'd set it up in PyTorch. And it might be boring to some, but maybe it's good as a refresher. Okay. So this is from the PyTorch Quick Start guide. The first thing you do is you set up your data set. You say, data loader, here's my NumPy array or whatever it is. And you say, okay, give it to the data loader so that it can turn it into an iterator. So you can go into the, you can take data of size, batch size out of it, right? So you have the training and the test data loader. So that's the first thing you do. And the second thing you do is you make your neural network. So you have to subclass nn.module, and then you have the constructor where you set up all the things you need. Here in this case, they have all the different layers you need. And then this is the forward where you send in your training data, and you should get the prediction back, right? And then here you just create the model. So I mean, this is like standard PyTorch, right? So in it, where you set it up, and then forward is where you run the data through your network, and whatever comes out, you send it back, and then everything else is taken care of. You don't have to worry about other stuff. Well, I mean, at least for the network part. Okay, so that's the second step. The third step is you say, okay, I need a loss function of some sort, and then an optimizer that will look at the loss function and calculate the gradient, and then update the parameters, right? So that's the third step. And then the fourth step is this training loop that you have to do. So you go over, this is the data loader from your training, and you have the X and the Y, the actual value, and then the data and the actual value. And then you pass it through the model, get the loss, ask the optimizer to zero gradient means do the calculate the gradient again. Otherwise, you will remember it from the last time. So this is always like some boilerplate that you put in there. And then you say, okay, we did this forward here. Let's do the backwards. So you calculate all the gradients, and then optimizer, tell the optimizer to now update the parameters by, change it to the direction that you calculate the backwards in. And then usually after a certain epochs, you kind of print out the loss just to make sure that it's actually going down and not stuck or going up, right? So that's the whole idea. And there's this also last step that you can do is you can, after you've trained it a while, you can also measure it against the test. So which is almost the same exact method, but you just make sure you normalize it over the size, because otherwise it's hard to it's not easy to compare. So right, it's yeah, I know Fast AI wraps all this this up. I remember I've only taken the first 1 or 2 lectures, but they wrap it up so that you don't have to see it, but the homework is done with PyTorch. So those are like the 4 steps we have to do, right? Okay, so let's get back to it. So let's look at the first step that we have to do. So oh, let me go back here to the homework. In the homework, oh, where did it go? In the homework, we're asked to fill up this function. So we will get the training data, the test data, the D, and then the D set ID. So this, I don't think it's used. So it's very vague about what this means also. But I don't see it used in the solution also. And our obligation is to return a NumPy array of train losses. So every batch we have to make an array of training losses, and then the corresponding test losses for every training loss we found. And then the actual histogram of size D. So for each value, we have to give a probability, right? Okay, so we have to follow the same 4 steps that we did before, right? So here. Here's this. This is the solution. So you ask the data loader to make a training and a test loader. So all you say is batch size. So it turns the NumPy array into something iterable. So that's the first step we do. So since this is a NumPy array, so this is just 2 lines and we're done. And then the next step is to create the model. So we have the histogram network. So you can look at it. So in the constructor, we have thetas. It's called logits. That's what's used in the homework. But these are the thetas. And then we set it all to 0. And then the size is D, which is the number of bins in the number of bins in the histogram. And we say requires corrected so that it will backpropagate. In the solution, there's no forward because it's not needed. There is the forward is needed to do the prediction, but since the training set already is kind of a histogram already, you can make a histogram out of it. So we just have the loss function, and this is not from the NN module. This is just a function that's added. So we could have put it outside, but it's just in here now. And then the loss function is that it's a cross entropy of our distribution and then the distribution of the training data. So it's done in a weird way here. So our distribution is turned into it's repeated over as many data points as we got. So in this case, if we got 128, because that's the batch size, so it would be 20 or D by 128. And then this cross entropy will, first one will take the logits here, and then the second one will take the numbers here and then do the cross entropy. So you don't actually, you don't have to give the 2 distributions. So it's a different format way of giving the same data. Right. So so the second step is to create the histogram. So that is the step here. Okay, and then this part is just this is the stuff that we have to return. So we have to give a training loss and the test loss. So just create an array, and then the test loss is the loss when we first start out. So this is our model, which is all zeros right now. And then this is the test loader. So this is the test data. So if we look at the eval loss, all it's doing is the same thing as in the tutorial. So all it does is go through each point in the data loader, right? So we'll go through the data loader and say, okay, give me the next one. And then you calculate the loss, you add the loss, but you multiply it by the length. And then after that, you average it out again by the length. So you get an sort of average loss. Okay, so we have the loss function here. That's already part of histogram also. And so next step is to make the optimizer. And so we use Atom. I think that's what's also used. So you could do stochastic gradient descent also, but so SGD is also here, but let's just use Atom. And you have to give it the learning rate and then all the parameters that you want to optimize. And here's the again the boilerplate PyTorch. So you go over the epochs. And then this is a train function that's been created here in the. So this is going with the solution. And this is where that boilerplate function is actually going on. So for each data in the train loader, we calculate the loss. We say optimizer, zero gradient, remove the last calculation. Let's go do back propagation. And then whatever data we got, we'll store it because we have to send it back. And then the optimizer change, make a step in the direction of the gradient, right? And so that's just, this is basic, basic PyTorch. And so we get the losses and we add it to our arrays so that we can send it back. And then once all of this is done, then we just send it back, right? Okay, so let me run it real quick. This is small enough so it just can do it on the CPU. So yep. So let's look at the first one. And this is a similar diagram to the one that's given in the solution. Final loss 0.2553, 2.064. We can see that the test loss goes down and stays pretty quickly, but then it this fluctuates, and this is fitting to the training data. Although it has a theta for each bin, it can't quite fit it. And then I added one extra thing to it to see how it fits the test data. So this is for the training data. It's still called train data, but it's actually for the test data. So you can see how the distributions fitted. Does that make sense? I think it's pretty standard PyTorch stuff here.
So essentially, you're finding f as a function. It's like a set of parameters for the function f to convert x to y, basically, right? That's what you're doing.
Yep.
Yeah.
All it is just you have a histogram and say here's all the thetas for a theta for each each
Right,
bin,
right. Each of the Ds, right?
Yeah.
So okay.
each of the Ds, and then just do back propagation. And it doesn't quite, like, you'd say like, well, why isn't it perfect? Like you're training on the same exact data, right? So I think it's because our batch size is 128 and our data is actually 1,000. So if we said 1,000, or it's actually 800, but anyway, if we said 1,000, that our batch size is going to be the entire histogram, then we'll have a different result.
Yeah, it's also due to randomness when you start, right? Because all these neural networks are initialized randomly. So unless you fix that, you will never get the same result.
Yeah.
Actually, here we initialize it with 0. It's not a neural network at all, because we just feed a bunch of parameters to the histogram. So we find in the logits which would correspond to this probability distribution. We don't have actually like, so the mapping here is like a number to log it, like direct lookup into this our theta parameter. So
okay.
no neural network here.
I see. Okay. So it's like a 100D approximation of this smooth function, right? So it's got 100 steps or whatever D is.
Yep. Yep. Yeah, it matches up with the actual distribution. So it's yeah, there's no neural network. It's all it is just a back propagation and optimization. And so if we make the batch size large enough that all of the data is in the same batch, then we can see that there's none of that. It will fit the data perfectly, but then obviously it doesn't quite match the test data. But it's probably just characteristic of how the algorithm works. 120.
I guess you can get better results by tuning learning rate. So in the first case, you kind of underfit it, and in the second case, you kind of overfit it.
Okay. Yep. Can try this. Yeah, it's fast enough, but yeah. It's pretty good. It's a little bit off, but yeah, it's pretty good.
Yeah, but we cannot do perfectly here because, the test distribution and train, if test distribution doesn't exactly match the train distribution and we don't have like actual distribution from which we sample, so we cannot do better than like approximating the train distribution. So.
Okay. Okay. Yeah. So that's the part A, and then part B is similar, but with the other one. 100 values, right? 100 D values. So it took a little bit longer, and so it's fitting to this one, and there's that site noisiness because of our so that size is smaller than that distribution. So it always is like fitting to one, fitting to the other, fitting to the one. So it's always a little bit off, but and this it fits pretty well. And then this is it. It doesn't quite fit the testing data. So yeah, it's just practice in stochastic gradient and how to use PyTorch, right? So this problem.
Yeah, one small comment here.
Sure.
Instead of repeat, you can use expand as in that where you like compute the loss. So,
up here.
Yeah. No, in the here. So where you returns it. So instead of repeat, you can use expand, and that would not create. So repeat creates a copies of the same tensor, right? And expand just kind of emulates those copies. And here we have like a single tensor, so we can expand. Basically, that's kind of command or method which underlies broadcasting, if you know.
Okay. Yeah.
So as just a minor thing, it shouldn't affect result in any way.
Okay. Yeah, it's throwing some sort of error, but anyway.
Yeah, maybe yeah. Like need to change parameters or something like
okay,
that.
Yeah, it's target size something. Okay, well, I can do that. I'll make a note of it. Expand versus repeat. Okay, so yeah, it's that one is pretty straightforward. Now it gets slightly more complicated and a little bit more, just a little bit more, and then okay. So the next problem is so instead of using theta for each of the histograms, right? So if we have 100 bins, let's use 10 thetas. So we're asked to use a mixture of 4 logistics. For logistics, and here's the formula for it. And for the edge case, when x is 0, we have to replace it by replace x minus 0.5 by negative infinity, and x these two edge cases, right? So yeah, so it's was a little bit confused, but here I think the paper has is from the Pixel. This is the Pixel CNN paper, so they have this formula illustration, which I it was so what I was confused about was it said p theta of x, and I was like, where's theta? And what actually are we parameterizing? But in this one, it's p of x given theta, pi, mu, and s, right? So we have k pi's, k mu's, and k s's. So since k here is 4, we're supposed to be 4 logistics. So here's so we'll go back to this problem. So when we make the network, so this is the mixture of logistics network, we need the logits, which is the thetas, I guess. These thetas are the logits. And then we need the means. So logits, which is just nmix. Nmix is 4 here, the number of mixtures that we're using. This 4 comes from this 4 right here. So there's 4 of these mixture of logistics. And it's set, all of them are set to 0, and these are the means. And they are set to some, just a, it's not random, but it's something else. I think it's like 1, 2, or it's divided by this. So
yeah, on this one, Martin, just FYI, it took me at least while I was a conceptual understanding to get some better understanding of even discretized mix and how any discretized mix of logistics gives any shape. There's a bunch of blog posts and code that I refer to, and I'll post that after we're done with the discussion. That really helps get an understanding of not so much the answer to this problem as much as the answer to how does discretized mix of logistics, and in fact he starts it with a discretized mix of Gaussian models, leads to the ability to model any curve or shape. Right?
Okay.
And that involves moving from a probability distribution to a cumulative distribution and back again, which is kind of part of the code. So I'll post those links once we are done with the discussion.
Okay, yeah, that would be great. Because here in our case, what we'll just end up doing is just implementing that formula in the forward
Right.
part and not really knowing like, okay, what does it actually look like? What are we actually mixing together? Oh yeah, and I was gonna say what the means are. Yeah, it seems like it's yeah, it's 0, 6.66, 13.33, 20.
Yeah, so to your point, I think the means, if you look at the code, divides the range of it. So when it's 4 or whatever the n mix is, it just divides it up into equal parts. That's why it divides the range of n mix by n mix minus 1. So if you have 4, then you have 0, 1, 2, 3, and then each of them divided by 3. So it, that's what it does. So if you have 5, then each of them, then there are 4 equal parts between the 5 points. If it's 4, then there are 3 equal divisions between those points. So that's what it locates the means. That's what it starts off, the self.means code.
Okay. Yeah, it's probably so that the centers are in, so this point, like 4 different peaks. So they're not all in the same
yeah,
place.
not corresponding to the graph you're pointing at, but corresponding to the mixtures that we are creating.
Yep. Okay. So yeah, that makes sense. And then the log scales are random, right? So n mix here is 4, and then it's just 4 random numbers. So let's see, I'll probably end up going somewhere else.
Yeah, so the log scale is kind of the variance that, and it's taken to be the log in order to keep the variance positive. That's why it's a log scale. So scales is just the standard deviation or a variance, and we take the log of it and make it log scale just so as to ensure that the scale is always positive.
Okay. Yep, and so it's the same process here again. Oh yeah, before go there, let me oh, there's nothing there. Okay. The model, it just shows mixture of logistics. Okay, and then what was I gonna say? Yep, this one, the forward part. So here there's at least to me, what was going. This formula here, here. So x, or the other one, sorry. These two, x plus and x minus. And then the inf scales are the SIs, but instead of dividing by SIs, it's exponential of the negative of the log scales, which is just the log scales that we created, the random values. So I guess it doesn't matter if you're dividing or multiplying, but you take the exponential of it. And so then there's the sigmoid of both of these. It's the same one, right? Sigmoid of the whole thing, this part, and then the sigmoid of this part, and then the subtraction. So I'll switch back again. So this is the subtraction between these two. Okay, and now it becomes a little bit not clear to me. So they do take the log of it, and then they clamp it and take the log of it. So clamping, I believe, means okay. So there's no help here. yeah, this is the minimum value that it can take in this CDF delta. It's not allowed to become smaller than this value. And then they take the log of it, and then they clamp some other stuff. So here all of it goes into making sure that the condition that was given in the homework, that if it's x is too small or if it is too big, then it has to be infinity.
It might be for numerical stability, the clamp, because log 0 is it blows up, undefined, maybe.
Yeah, that's what it is. Yeah, it is for that purpose. And also, this is the part, and I'll post the links, as I said. This is the part where if you go through the code and the links that Posh you figure out, and I'll just explain conceptually, it's moving from a probability distribution to the, which is where you take the plus minus 0.5 to the corresponding cumulative distribution of the probability distribution. That's why the notation says CDF. And you move to the corresponding CDF, which is kind of the integration of the probability distributions, and then do the, and I'm still, I have to go through this a couple of times to get it in my head as to, the probability world and what it means to do it there. But that's the reason that you see the terms, the CDF. One other detail, just in case you're working through the code line by line, as I was trying to do, which threw me off for a while until I figured out something. So let me just mention that. If you see, he uses the term CDF plus, but actually does 0.5 minus means, and then CDF min, and then he does D minus 1.5 minus means. And then if you look at the line where Moten has the debug or the lamp thing highlighted, then he throws the CDF plus when its x is less than 0.001. I personally think that the terminology should be reversed. That makes, at least to me, more sense. But because he puts the plus where it is in the torch.where, it doesn't matter. But it's kind of strange that log CDF plus, he takes it corresponding to 0.5 minus means. And if you work through the math, at least to me, it makes more sense to call this log CDF min and the other one log CDF plus, because you're doing it corresponding to the value minus means and the value plus means, or at least D minus 1.5 minus means, which means you're on the other side or the right side of what the distribution, the 0.5 and the, add the 1 but subtract from D in the means. But because of the way that he constructs the torch.where, where he puts the plus on the x less than 0.001, it doesn't really matter what he calls these two. But that took me a while to get because of the naming and what I was expecting the values and where they are to show up. But anyway, that's just FYI if you work through the details and follow along on the code, because somebody has actually implemented the code, I forget whether it was for CNN Plus, and been asked the question of, I don't quite understand what you are doing in the equivalent code that we are staring at, and he's gone through a long explanation as to why, and that gives, at least to me, as close to explanation for why or the math underlying what's being done here. And I'll post that link.
Okay. Yeah. Thank you. Yeah.
Also, the original Pixel CNN++ repo, it contains a code for implementing this stuff, but in TensorFlow. So probably it could be useful to understand their code. Also, it's not quite the same problem they solve there, because there it is used to approximate this distribution for actual pictures, like pixels. But yeah, still they have.
Yeah, that I haven't looked at it, Artu, but I doubt that first pass. My reaction would be that I don't know that that matters, other than in the setup, obviously, because you would probably use a different number of mixes, and I don't know whether they start with different mean points and scales, but the rest of it in terms of the math should be similar. But anyway, I think to your point, we'll have to look at that code to see whether
there are some nuances connected to the shapes of the, like basically what inputs you take and stuff like that. So because the implementation is designed to work with the outputs of like actual neural network, and we are trying just to fit the histogram. So basically our thing might be a bit
yeah, so the X might be different is what you're saying. X values could be in a different range and stuff like that, because here you're just choosing X less than 0.001 and then X greater than D minus 1 minus 1 is what? 23. So, okay, got it.
Okay, yeah, so, and then there's this last part, which is the logits. Logits where the theta is here, right? So we have to multiply by the theta. And so it's just added because everything is in log, I believe, right? So we have a log softmax, and then the log probs are added to the pi log probs are added to the x log probs, and then we return the log sum exponential.
The one comment there I would make, my understanding is, and that was a question, again, if people already know it or after going through the links and stuff can post in Slack the answer. One particular thing that I didn't quite follow, a comment and then a question. The comment is, I think the log props, the fact that it adds the x log props, which is the line prior to the one that you have highlighted, and then there is the pi log props, which is the log softmax. The fact that those two logs are being added says that actually the two values are being multiplied, right? Because when you add two logs, you're actually multiplying the two underlying values.
Yep.
That you're taken. So the line you have highlighted is actually the multiplication of the two underlying values of the prior two lines. Then the question I have is, at least in the logistic mixture or the few lines from the Pixel CNN paper, that just seems to be the pi log probs, the x log prop. But I am somewhat at a loss as to where the logic or explanation is for multiplying that with the pi log props. Is that just the pi value that you see in that equation that you showed from the paper? Is that what? If you go back, yeah. So is it just simply this pi I that is being calculated?
Yeah, it's just this pi I. I think this is difference, right? The something difference, and then you just multiply it for all of the keys. The pi I.
Okay.
There's a softmax.
And you take the log of both, therefore you add the log of the two.
Yeah.
Okay.
And then, I think, sorry.
Go ahead.
No, I think pi I is the amount of each histogram or each Gaussian that you're giving in, right? Yep. Each of these, the distributions, how much of it to use, right? So I think that's
okay. So each of the four distributions, what proportion of that or what fraction of that to combine in the mix to generate what you're after.
Exactly. Yeah.
Okay, got it.
I think this is like the mean, the standard deviation, and then the mixture ratio, or weight. I should say weight.
Yeah.
Mean and
the weights of the discretized mixture that you're using to generate the curve. Okay.
Okay. Yeah, and then I think this is the log sum. X is it sums the logs and does the exponential. Yeah. Can, but then we do get the data back. Okay, and the loss itself is just the mean of X. So don't know how that works out, but okay, yeah. And the distribution is look at how they did this here. I think this is same from the homework. I don't know if I messed it up or. This is this first part. Yeah, so this is the same one. So to get the distribution, it seems to just do the X and X. Self.d. Yeah, I'm not sure. So probably being used some other way here. But okay. But
what is, again, sorry, in this case, what is we are in creating. So D is still the value of the points, the range, like, you know, it was 20 for the first graph, so, or 100 for the second. It's still the same integer range for the values. That's what D is.
Yep, because the distribution has to be given for each. You have to give the same output as the before one, a probability for each value in D.
So that's why here you take the exponent, and then in your forward and stuff, because you're doing log sum, so by the time you get to log probs and then take the log sum, it will become the log of the exponent and therefore return you the actual values. So that's why it works.
Yeah, I'm not sure, because it's not using any of the actual values from it's not using any of those three values here, the logits, means, or log scales, to calculate the distribution. So
yeah, but those get converted through this torch.where, right? So it converts the x's to these values. I'm saying the distribution is self.x.exponent, because you exponentiate the x values, and that's what you take as the distribution from the output. And I was just trying to match that with why we would exponentiate. We would do that if the values we are getting as the outputs are the log values, because then that's what will ensure that we are getting terms similar to x, because we want the output, given that this is all input equals output, so we want our output to be the same as the input. That's probably why we exponentiate, because we expect the output to be the log, output of our model to be the log of the input. Am I making sense, or does that make sense? So anybody care to comment on whether I'm right or wrong?
yeah, let's see. Just maybe it's never called, but
no, I think we would need the distribution, right? Because
so we from our model we get logs of probabilities, so logits, and we need to exponentiate them to get a proper distribution, because our output of the model, so here it calls self with x. X is just weirdly gotten tensor of from 0 to D, and
right.
and we get logits from model and then we exponentiate to get a distribution. I'm not sure what your confusion is here. My confusion is why don't use torch arrange and instead do float tensor of NP arrange. That's all.
Oh, I see what's going on.
No, but actually, it's not confusion as much as exactly confirming what you just said, that our output of the model is a logit, therefore we exponentiate to get a distribution. That's my understanding, and I just wanted to confirm that.
I think you're right. Yeah. Right.
So this is just taking each value and doing prediction. Yeah, I don't know why exponential. Yeah.
No, that's why I was saying exponentiate because of what Arto just said, right? Because our output is a logit, and then in order to get a distribution from that, we convert it to, we have to exponentiate. Our outputs are log values, so we exponentiate them to get the distribution. But what was your comment, Arto? I didn't quite catch that.
Which comment?
No, you said something about.
Yeah, so I don't know. For some reason here is used torch float tensor of NP arrange D, and we could just do torch arrange self D. That's all. Is it not much of a comment, but
Okay, but is it because we want will torch arrange give you integers versus float, and then you need to do dot float? I know it's a nit,
maybe,
but I'm just asking.
I think by default it it doesn't matter. You can just specify the data type you want.
Okay.
For any tensor, or call the float. Yeah. My comment is about why use numpy inside of torch. If you could just use torch, but that's not at all important.
Okay. Yeah, and then I'm not sure why the taking the mean of the prediction is a good enough loss function, but
so basically we are trying to get a negative log likelihood loss, right? And our model outputs log probabilities, and we just need to take a mean of those negative mean, so that would give us negative log likelihood. So basically, what negative log likelihood is? Negative logarithm of probability of the actual class, right? If you imagine like probability of x. And we get a negative logarithm of that probability, that would give us negative log likelihood. And that's a standard loss function we use in many cases. Basically, when you use an n cross entropy or in torch or wherever you use it, behind the scene, you just do log sum x plus like negative log likelihood, this loss. So that's cross entropy. It's combination of not log sum x, but log softmax. And and here we already have the this logits, and we just need to get a negative sum. So I guess that's how it works.
It'll also be normalizing, right? I mean, because your forward returns you a vector, and now you want one number out of this for, so you basically divide by n.
Yeah, you need a vector because you get to call backward on it, and not a vector, you need a scalar because you get to call backward on it, and you need a scalar.
Okay, yeah, that That makes sense. Yeah, some of it is a little bit hidden. Yeah, they're probably they're equivalent, but it might not be obvious. Okay. And is there anything else on this one? I think that's it. So I can I think it works fine if I just run it. Produces these. Oh, I produced too much. I used 2000, but I think there's more data than this. Then it gets the same results, similar results. Okay.
Yeah, I was wondering, and I didn't get around to playing it, if you give it, say, 2 discretized mix or 10 discretized mix, how that thing varies. I would expect with 2 for it not to be able to, and for 10, I guess it doesn't really matter beyond 4, but I was just curious. I haven't played with it, but just a comment.
Oh, okay. Yeah, I can do 2, but you'd have to do more, 4. You'll probably smooth it out. Can try the n mix equals 1 and use the second one and see what it does. This one. Oh, I don't need the local. Okay. Oh, done some to 1. It says. Okay, I'll just. Oh, I can't. Distribution norm. np.norm or normalize.
Let's just try it with 2, so we don't instead of 4 and see what.
Oh, okay. Still not okay. Yep. I don't know.
It because it becomes.
Oh, it's not nan. Okay.
Nuns.
That's the problem. Oh, sorry. I'll set it to 2. I thought it was because of something else. Okay. It didn't work. Yeah. So it seems the testing error is not showing up. Yeah, it didn't work that well either.
Yeah, so it seems, and I don't know, maybe we can try it with like 7 or 8. But 2 definitely doesn't seem to be enough to model the distribution, right, from that.
Or does it even work with 4? I never tried it. Okay, it works with 4, but doesn't work with 3. It's like this. Yeah, yeah, it works with more than. Yeah, so I guess you can try it out. See if there's ways to actually see the see the actual the logics being created. What each one is applying. Like when you have these 2, we can just have the other individual contributions. Oh, it worked here.
So what's interesting then is there seems to be some lower bound on the number of discretized mix that you need in order to model a distribution.
It probably was the batch size also. I changed the batch size to be really small. And 2 worked
so
now.
with 2 and batch size 128, it seems to model it okay, or?
Yeah, this seems to work. Let me try 1. This is again probably a nan.
1 I doubt will give.
Loss is nan.
It gives you not,
Yeah, the loss is nan. But yeah, okay. 2 should be fine. I can try and make a 3 version of the data.
No, that's okay. I mean, we will not spend time here. We can move on.
No, oh, 3 didn't work. So okay, 3 kind of messed up. it did this. So yeah, can figure it out. So I'll take a note of it. Okay, so I think this is all for question number 1. Yep, and yeah, if we have the links for the theory behind the logic, then
yeah, I'll post that as soon as we're done here. I have to collect them from where I bookmark them, and I'll post them shortly on Slack.
Okay. Yeah. Okay. Then we'll go to question number 2. Okay, and now things get very unclear to me. So, okay, so here we're going to use made, and if we remember made, it's this one, right? So you have the base net, and so x2 can only depend on some previous x1. And so it can't depend on x2, but I guess it can depend on the intermediate x2s, but not the initial x2. And so, okay, so let me look at the question. Oh, where did it go? Okay, the first one is the actual data. What are we actually doing? So if we look at the code here, visualize data, and it's actually reading a JPEG file. Oops. And then from what I've seen is that it's taking random points. So from what I can gather is that this, we're given a 2D distribution. So we have instead of 1D and then the plots, we have a 2D base, and then the color is the distribution. And it's this, it could be grayscale, I believe. It's not an RGB, so it's just a different way that this is being shown. But these colors are just different intensities. That's being shown, I believe. And the way data shows up is I can break here, and so oh, next one, data. So it is just a pair of numbers like this one, just pair of numbers. And then the frequency at which these numbers show up will determine the height of that pixel and the intensity of the pixel. Right, so the brightest spot would show up a lot of times in this data. So if 0, 0 is very bright, it would show up a lot of times here. And if it's dark, it would show up not that many times. And it's being randomly sampled here. Right, and then depending on the intensity of that pixels somewhere. I think. And so when it's being plotted, it's the distribution, and this is calculated as so whenever the data becomes X and Y, you look at the data, then you add +1, and then you normalize it, and that's your distribution, and that's what you're plotting, right? So it's the same histogram, same style, but just in 2D form. and the 2D base is the location, and then the color is the height. So the lighter the color, the lighter the color, the higher it is. But it's sampled from an actual picture. So the smiley face and this picture. And so this is the test data. This is a smaller sample of this one. So it has some of the characteristics, but not all of it. Okay. Okay, so this is, I guess this is just an extension of the same problem. So implement and train made model to maximum likelihood. And then you have Px0, x1, so x or xy, I guess, on the given data set with any autoregressive ordering of your choosing. Okay, so let's go back to how to the same. We can just go over some of these parts here. This part right here. So he made an element. I don't know what this is called, but it's one part of the neural network where we store the mask. So we have a number of features. So this is just a linear, right? So linear means you have number of inputs coming in, and then you have to send out some outputs. So you get the in features and the out features, and then biases if you want to add some value to it. So it's just the AX plus B, and then in features is the M, and then the out is the the other way around. Yeah. Right. So also here is storing a mask. So this buffer in PyTorch means that you can store a value in PyTorch, and you don't need to have to backpropagate it. It's basically a constant value, right? And this is just called mask, and it's the same size as the features, but without the bias. And this set mask is just data copy. It's just copying whatever mask is into our buffer. Self-mask mask.data. So this mask and this mask, and we're just copying it whatever we have. Okay, and when we do the forward part of it, we get the mask, and then we just I just put it there to look at the mask, but we do the same thing as a linear would do, except so the linear would multiply the date input and the weight and then add the bias, but we also multiply the mask with the weight, so that if the mask is 0, then that weight is zeroed out. So that, like the same idea as in made, right? So this is the previous video, that we have to cut out some of these connections, and so the mask would cancel them out. So each linear layer now, let me go a little bit further back. Yeah, each linear will have the bold ones are the ones that have mask 1, and then the lighter ones are the ones that have mask 0. So, but it's still the fully connected linear layer, and except for this one doesn't have any connection, or maybe it can't. It can't go backwards. Okay. So I guess in this that would also have to be masked out, because this is a linear layer and it would connect everything to everything, I believe. Okay. Yep. So this is the small bit of it, and then this is the actual model that's made from the NN module. So here, I think it's it's a little complicated because it gives the input shape. Here in our case, it's just one picture, but you could also have. So this is also catering to the future homework. Here we just have this one picture, but then in the future we can also have an array of pictures. So so the input shape can be can have different sizes, and D is the same as previous. How many steps each value can have. So so it's it's the I guess. Oh, I'm not quite sure what it is now.
Is it the dimensions, if you will, or the values? The range of values for each of those, meaning, you know, when you showed that two arrayed X, Y values, it's the range of those values. You know, when you had those two columns next to each other. When you just showed us the, you know, you showed that two columns of X and X1 and X2 or X0 and X1 or whatever that you had.
I've already got
it.
But no, that one only has the coordinates. So, but here in this case, it's 2 again. So,
but what about the values inside of those? Isn't D, I thought, was the range of that, or am I?
Okay, wrong? Yeah, that's probably true. Yeah, how many it can have at most.
Yes.
Yeah. So if it was a pixel of grayscale, then the max it could have is 255. And since this is grayscale, so it only has 2. So that means.
Yeah, so it'll be 0 or 1, or, you know, that's what I was thinking. Does that make sense?
Yep, yeah, that makes sense. Yeah, here in this case, the D would be, yeah. So if I run this again, it would be probably 256 because that's a grayscale. Didn't work. Okay, let's just see what the D is. Oh, now it's doing it.
Just 25.
25. Okay, that's probably just a number of levels that's been discretized to. Yep, and so yep, if I go one more step here and okay, this is for constructing the mask matrix. Okay, that probably should go to that one next. So here we create the number of layers. It's dependent on the HS, which comes from NIN, which comes from the input shape, and the input shape is so in our case it's 2 comma, meaning that it's a two-dimensional.
Sorry, question. So since they do N out is N times D, so, and if you go back to the sorry, if you go up to where things are initialized.
Okay. I'm sorry. Yeah. Okay. Yeah.
Little further up. Yeah. So you see, self NN is just NP product, which means that you would flatten that and thereby get, you know, because input shape is 2D, but you have to flatten the 2D, right? Because we flatten the image and then provide it even for MNIST, if it's 28 by 28, you flatten it and provide it as a linear input to the input path, right? So that's the product of the input shape is just flattening it, correct? And then when you do the, does that make sense?
No, I think it's not the size of the input. It's the, well, the size of the input is actually 2D. So it's XY, 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 XY.
Right, but what I mean is the
flatten
dimensions
here.
of,
so
sorry, go
this
ahead,
is the,
Yeah, so we are dealing is like standard fully connected network here. So it can only accept a flat input. So if you have, say, input of shape 25 by 25, actually you want to input a vector of 25 squared long vector into your network. So you got to flatten it because it's just a fully connected network, right? We cannot feed it with an image.
Oh, so
right. So sorry, go ahead, Ojan.
Oh yeah, my point was the input is actually just X and Y. So this test data right here. This is the input. This is just 2 at a time.
True. That's true, but we need to output distribution. So our input is just this two variables, but we need to output a distribution. So
it's 25. Yeah, we need 25.
So yeah. So, but what I was saying was, if you go back to the initialization part, again, I was just making the comment that isn't that NP prod basically flattening the input to where you make the N in the flattened stuff so that you can provide that. And then the self out, if you go to the next line, it just multiplies the N in. So that means each of those with kind of D, and D therefore is the, whatever you want to call it, the intensity or the range of values that each input can take, because you will need that as part of your, that's what you will want to output.
Yep. Okay. Yep. Yeah. I was.
I had, sorry, one question I had in the initialization itself, and if we haven't yet gotten there, then I'll hold. But regarding the ordering, but if you have other things, if you're covering other things, let's proceed.
Oh yeah,
we'll come back.
Just a small note was that when we do the MNIST, the size is 1 H and W. So each row is actually an image. So
okay.
So it's a little.
So
bit.
here you provide, but why is the first in this single image case you get just 2 comma, so it's a tuple of 2 values. That's why it's a 2 comma, and in this case it's each one is 21 by 28 by 28. So that's what 1 HW stands for. Is that right?
Yep. Let me run real quick.
Yeah, I believe so. Okay.
So that the that is my test data. Let's see. So it's 4091, 1, 20 by 20. So the 20 by 20 is the image, and then this is the
yeah. So the 4021 is whatever is the batch size. So it's batch size 1 HW, and in the other case it's batch size
times 2,
and just a 2 tuple, yeah, and a 2 tuple, or a tuple with 2 values basically. Okay.
Mm-hmm. So that gets a little bit confusing, because then in MNIST case we're like sending smaller images in, but here we're sending a pixel or something.
in MNIST case, we have like this 28 by 28 inputs, right? And in this case, we have only 2 inputs. So images are treated very differently in these 2 cases. So we are not treating this as an image, but as a distribution in the first case here. So we are basically learning this single image is a distribution itself. And in MNIST case, we are trying to learn the distribution for each pixel of the image in MNIST dataset. So each image is a sample in this case, and we are trying to learn the distribution of those data generating distribution. So that's
so what you're saying, Atto, if I gather, that's a good point, because what you're saying is here it's just single image, so we're just treating, or what we are after is just the distribution of the pixels in this one image. That's it. Whereas in MNIST, we are after the distribution of the pixels in each of the images that we then provide, and the overall distribution of the pixels, like per image or per class of the image, correct?
Yeah. So here you can, in the first exercise, you can just forget that that was an image and just treat it as like this 2-dimensional distribution. And in case of MNIST, we learn 784 dimensional distribution. So we will output a probability of being 0 or 1 in case of binarized MNIST for each pixel. And here we just, so what we learn this image, which is itself, like basically we converted it into a probability distribution. So each pixel in this image would have some kind of probability, and we are trying to learn that.
Could have just, yeah. I was going to say could have just randomly generated, but then you can't compare 2 of them, see how well they're doing.
Yeah, I know. So it's a nice face, smiley face, and Glen intense picture and stuff would probably be harder to make it a little more meaningful.
Yep. So that
I guess the reason to do that is it gives us a qualitative assessment by just looking at the output, right?
Yep.
How bad or good it is compared to the training data. Because otherwise, if it's random, we won't be able to kind of quite judge that like visually.
Mm-hmm. Okay. So let's see. So this. Oh yeah, we're making the neural network, right? So so here let's go here. For each, we're making H0 and H1, HS. Let's see, HS is here. So the first one will start at 50, then goes to 100, then becomes the hidden layer is 100 by 100, and then the output is 50. So so this is the layer that's made, and so I'll just jump over here for the time being.
Sorry, why do you say 100 when it's actually given as 512, or what am I missing?
Oh, that's the default value. Sorry, yeah. This is the default value. So we set it to 100 here somewhere.
Okay.
Here.
So when we input is provided as 100,
Yep,
100. Okay,
yep.
okay.
Yeah, it's just the default. So
Yep.
And so if we look at the printout of the network, we can see that it's a mask linear. So input goes to 50, then goes to 100. There's a ReLU, then 100, 100, because that's the hidden one, and then the output goes from 100 back to 50. And yeah, and so that's the network we're creating. So the next one to look at is in each mask linear, what is the mask that's being created, right? So so that's the next interesting thing to look at, because that's also in the initialization here. These are where the masks are being made, the create mask function. And each layer has their own mask, right? So the first one and the second one and the third one have their own masks. So here we've created the layers. Right now they don't have any masks. So we go here and then we create the masks. And so if I go here, from here we go to create mask, and okay, and so this M right here that they creates is a random is some sort of random. So
is it a set or a tuple when they do the self? I mean, sorry, or a dict there. I haven't fiddled around yet with this part to figure out. You know, when they say self.m is those curly things, that are they initializing a dictionary of values or a tuple of values?
Which one? This one?
Up above when they say self.m is, yeah. That
oh, one. Okay. I don't know.
Is that a dict? It seems like it, right? Because it's a dict. Okay.
Yeah, it's a dictionary. I think it's for the different layers. There's 3 layers, right? So they have it for let's see, self.
Okay.
Maybe that's what it is.
No, that's
so
a good
-1,
guess.
0, and
probably.
1. Yeah. Okay. So let me just do this, and there's the masks array, and there's the 0, 1, and 2. There's the three masks that's going to get applied. And if we look at the masks, it's very big. So it's true means a 1, and then the top half is true, and then it's false below. For the first one, for the second one, it's all true. And for the third one, it's left half is false and the right half is true. So I'm not quite sure why.
Does it make sense in terms of what the pixels are allowed to look at? If we were to draw the full, if we were to look back at the lecture diagram, isn't this somewhat corresponding to, like he says, the type? I mean, it's not exactly, but type A, type B, in the sense that you would want, see, the second mask where it goes from hidden to hidden, then I'm just thinking that there is no restriction, right? Because everything can go to everything according to this, when you look at this diagram, right?
Mm-hmm.
The hidden layer is between, not the input coming in, but between the 2 hidden layers. So it's like the first set of zeros or nodes to the second set of nodes, in which case all connections seem to be allowed, correct?
Yeah, but
so that would mean your middle layer, where everything is true, makes sense, right? When you match it to this diagram. Now, what's more interesting is to figure out how the mask works for the last layer, which is the last hidden layer going to the output, and then the first layer, which is our input layer going to the input. So those are the interesting cases. But does that make sense, that the hidden to hidden, everything is allowed? That's why it's true for everything?
I believe so. So that could be. So here, the first 25, I think there's only 2. So in this case, there's only x1. In our case, there's only x1 and x2, right? There's only
correct. Yeah, but more from a layer standpoint. I mean, we can forget the how much inputs x1 to xn doesn't matter. It's more the layer thing and the masking that we are concerned about, right? Focused on right now, right? So, so do you, yeah, I'm just wondering whether everybody agrees that the reason for this middle thing, as you showed, and that's a good visualization that you have of the mask, is it's everything to everything. So the question is, what is it for the very first input layer? You said, what was your observation with respect to the first mask layer?
So I don't, I'm not quite sure if this is set to the first layer or to the which layer it goes in, because it's it creates over the layers self.modules. So yeah.
So if you mark 0, 1, 2 as indices 0, 1, 2, then I would imagine it is in the sequence of masking for the input to hidden, then, because there are just 3 layers, right? So input to hidden will be the first mask, hidden to hidden second mask, and hidden to output third mask.
Yep. So but so here the hidden mask has all true, so it does not so in this case, so this layer, let's say we only have 3 layers, right? So we have 1, 2, 3 layers.
Yeah, it's just that, think of it as, imagine one of the zeros in the in between, or one of the nodes is gone. So we just have inputs going to circles, going to, forget the middle guy, going directly to the 1, 2, 3, the third nodes, and then going to the outputs.
Okay.
So that's kind of our equivalent, right? So anything in the middle, as we see here, is fully connected, meaning all inputs can go to all outputs. So therefore, everything being true is done. So now let's then focus on the input and how they get masked.
Yep. So either this one is the input or the other one is the input. So here.
No, I think it would be in a sequence. So probably the zeros would, again, that's a guess, but
okay.
Yeah, in fact, it shows you, right? It's 50 to 100. So 0 and the array 50 to 100. So that is the input.
Okay. Yeah, that makes sense. So here, 0, the first one is attached to, so 0 can go to 0, but 0 can't go to 1. So all of the weights from 0 to 1 are canceled out, right? Because this part is false.
Yeah, it might be useful to draw it, I guess. Like this, we have in our inputs here.
Okay.
So that's x0 and x1. Then we have like intermediate layer, and then we have outputs. So we want
actually, Arto, we have one more intermediate to intermediate and then out.
Yeah, but we just can
ignore
start
that.
with the very simplest case and then extend it to. So we want to predict x1 output to be conditioned on x0. So it would be like connected to everything, and but we cannot, like, basically this is our last input. We cannot condition on itself, right? So and in this case we have this information flow from x0 to x1. So x1 is conditioned on x0, but is not conditioned on itself, because it would like introduce an information leak. So it would like break autoregressive property, right? And x0 should be not conditioned on x0. So we can not connect here or here, and yeah, judging from what from that diagram we had in lecture, so it's done this way. So we don't connect it here, but connect here, right? So how do I erase everything? Let's try to add another layer, right? So if we have, okay, okay, now we have another hidden layer, right? And inputs here, so outputs here. So again, we like in the lecture, we have these connections here. But we cannot connect this one to any of the nodes which are connected to x0, because it would make 0 output conditioned on 0 input, and we don't want that, right? So these connections are forbidden, and but we can connect everything to here. If this one is connected here, this one is connected here, this one is connected here. So basically, our first output shouldn't be connected to the first output in any way, and the last output shouldn't be connected to the last input. And yeah, here we have like do we have this, if we have all true in the middle, right? We have all the connections here.
Mm-hmm.
Yep, that's the middle one.
Middle one is all true.
So in this case, we got to remove this connection. Where is eraser? Okay, so we get to remove this connection, and then we don't have any problem here. So in this simple case with the first, okay, we now can connect. Oh, sorry, I just did it the wrong way. So we can connect the first input to all the hidden outputs, and the second input we connect it to nothing. Then we have we can have a fully connected regular fully connected transition here. And then if we don't have any connection here, then we got no problem, right? So this explains this kind of connectivity.
Yeah.
Right, but how? I mean, I guess question is from the mask that we are seeing. So in the we get the middle layer is fully explained. The input layer, what is the nature of the mask you said, Martin?
So all of the ones are not connected to anything, right? So I also showed the X1 here. This is all of them. They're not allowed to connect to anything. So they're all the bottom.
Oh, because of the 20, because D is 25. So 25 on to 50 will not be connected to anything. Okay.
So that's why it's sitting here.
That's exactly what R told us.
Yep. And the third part is a little bit strange because so 0 to itself is not allowed. So only the second half is true. So I don't know what exactly it means. Like the right half is true.
So again, we connect nothing to the 0 output and connect everything to the first output.
Yeah. Okay. That's probably what it means. Yeah. Okay. Yeah, you're right. Yeah, that's what it means. So you don't need this output, right? So we already know what the.
Or nothing connected to it. Therefore, the left half is. So we have two outputs, right? And the left half is the 0th output, and the right half is the first output. And the left half, nothing is connected to it, so everything is false. And the right half, everything is connected, so we have all true. Okay, the mask makes sense.
Yeah. Yeah. And so the code is little bit. There's a randomization. So I think we're running out of time, but let me do this one. This mask is very interesting when we look at the other example. So instead of this one, the MNIST one, because I think that's where the complicated code is written. Let's see. Did I forget something? I forgot something. Okay, I forgot something. Make mask. Oh, I do have the. Okay, yeah. So these are the masks. So let's see one. So these are the. So our model. We haven't looked at the model yet. If I look at the masks, this is. Yeah, they have different shapes. Right. So some of these are false, some of them are not connected to others.
Yeah, this would become interesting because of what we just saw, right? It would be like in the 784 pixels, which are flattened, you know, and when it is in a 2D array, then it's easier to imagine because you can say anything above and anything to the left. But when they are flattened, then the only reference we have is the lecture made picture that we just went to, and kind of making that correspond to which of the 784 inputs are allowed. I mean, of course, it's sequential and incrementally goes down conditionally, like we saw, meaning, you know, x0 is not allowed to get into x1, but and x1 is not allowed to get itself, but can play into x2. So trying to make sense of the mass, but, you know, the reverse thing of how do you then code up the mass the way they have coded it is what to me would be the interesting thing, right? Because, you know, you'd have to kind of think through it and come up with the code which they've generated to ensure that the rules of auto-regression are followed. Because trying to make sense, what I'm, I guess, long-winded way of saying, trying to guess the mass like we did with the simple case by looking at the mass in this portrayal you have and corresponding it to the flattened network is going to be really hard.
Yeah, especially since they randomize the positions. So it's not like 1, then 2, then 3. All these positions are randomized here. In the last
which begs the exactly my question, which we can take up next time. I think, as you said, we are running out of time, but thanks for taking us through. I think it was really, at least to me, very useful and very insightful. So thanks a lot for that. And we'll continue with this next week. But I think the you know, the ordering and how they pick that, or, you know, the way he has the self.ordering is whatever. If an order, I guess it's just a question of if an ordering is given, take it, or else, you know, pick some random or pick some number or in the range between input and output. But that's where the, because what you're saying is the masking depends on the choice of your ordering.
Yeah.
Because if you're provided an order, then you have to mask in that order.
Yeah. So that's why this one doesn't look like a staircase, but like some are tall, some falls all over because I think
because it depends on what ordering you provide. Because that, depending on the order, then the mask starts from there and then follows auto-regression rules.
Yeah. I think if we just disable this, then we can see just the staircase pattern probably.
But then you would have to fix the ordering to be starting at 0 and then not randomize, I think, right?
Yeah, but he said you have to use multiple ordering somewhere in the homework.
Oh, yeah. If you need to probably generate multiple orders and then average them as he showed in the lecture, then you would have to have the ability built in, right? Otherwise, you can't do that.
Yeah, and I think that's why it's there. But for the first case, it doesn't matter because there's only 2 inputs. And, but this randomization still always does the same thing. So it looks more complicated because the reason is that it's also used for the second part. But yeah, we only have 5 minutes, but I'll
I think that's probably a good place to break, or else we'll get suddenly shut off like it happened to me. So thanks, Mojan. Appreciate it, and thanks for going through it. And we'll continue from here, and let's not worry about if it takes a couple more than what I planned. That's fine. I think it's useful to go through it in the level of detail that you just did and have the discussions, so we can understand truly what's going on in the code, then just brush through it. So I appreciate you spending the time and taking us through it, and I'll post the links. And thanks a lot, everybody, for joining on holiday weekend. Appreciate it.
Thank you. Some intense stuff here.
Yeah, very nice.
Yeah.
Thank you. Okay. See you next week.
Right.
Yeah. Thanks, Mojan.
Bye.
Bye.